Today we have quite a few second year students joining in as well. Welcome to all of you. Great to see your interest in astronomy and astrophysics. So maybe would you like to, second year students, would you like to just introduce yourselves very briefly? Just put on your camera on. I mean, with my memory, I'm not sure I'll remember with so many new faces together, but maybe just briefly, we'll take not more than about 5 minutes. Just tell us where you're from and maybe what interests you in astronomy and astrophysics. Kriti, you can start off, I think.
Hi, I'm Kriti, and I'm currently living in Pune, but I'm from Delhi,
Okay.
and I've been interested in. I mean, who isn't interested in space and stuff? So I've been interested in that since I was a kid, and that's why today I'm learning astrophysics.
Okay, excellent. Okay, Dipankar, where are you from?
I'm from Pune, and
you're from Pune. Okay.
Yeah, I have had an interest in astronomy for a long time.
Okay.
Fascination with it.
Okay.
And I just wanted to see what astrophysics has to offer, and do I want to continue in astronomy as a subject itself?
Okay. Okay. Excellent. Gaurav?
Even I am from Pune, and
Okay.
I am interested in space since I was a child. So.
Okay. Okay. And where did you, okay, you're from Pune, fine. Kamakshi?
Yeah, good morning, everyone. I'm Kamakshi and I'm from Dehradun. And I chose astronomy, the course, because I would like to make out a career out of astronomy. I would like to become an observational astronomer.
Okay, excellent. We don't hear too many people saying we want to become an observational astronomer. Usually people are more enamored by theory, but excellent to hear that. Where are you from? You said I didn't catch it.
I'm from Dehradun. Originally, I'm from a town in Haryana, but I moved to Dehradun.
Dehradun. Okay, excellent. Purva?
Hello, sir. I'm from Satara.
Okay, excellent.
I'm interested in space stuff.
Okay, very good. Amruta?
Good morning, everyone. I am originally from Pune, and I got interested in astronomy after I saw the Orion constellation, and since then I have been fascinated with stars and stuff, and want to pursue a career in astronomy.
Okay, excellent. Rakhi?
Sir, actually it's Pakhi.
Okay, sorry, I'm so sorry. I'm sorry.
I'm from Delhi, and I just really wanted to know more about astrophysics.
Okay, excellent. Okay. So now we have Mansi.
Hi, I'm Mansi. I'm currently living in Pune, but I'm actually from Delhi.
Okay.
And I just really like space.
Okay, excellent. So do you know our third year students you all have met before, or?
We haven't met before, but we have talked on the phone.
We haven't had the opportunity to talk to them face to face, but we had.
Okay, then maybe the third year students can also introduce themselves briefly, all of y'all, so that y'all know each other as well. So Sai, you want to say a little bit about yourself?
Yes. So hi everyone.
So maybe all of you put your videos on, just briefly. I know you have internet problems and may not be, so that we can see each other, all of y'all. Yeah. And I'll also take a gallery shot just for our record and I'll share it with you all. Okay. So Sai, continue.
So hi everyone, I'm Sai. I'm the third year student, and currently I'm majoring in environmental science, but I have chosen astronomy as my elective.
Okay, Sai, thank you very much. Ahan?
Hi, I'm Ahan Parsale. Even I'm majoring in physics, but astronomy is my elective of choice, and I am considering it as a potential career path too. I think I've spoken to most of you before.
Okay, excellent. Okay, Akirno?
Hi, I'm Akirno Kalri Chaudhary. My dad's an astronomer, and he has lots of books lying around, so I thought this would be the course that would, I'd have some background knowledge that would help me get me started. And I'm more interested in the mathematical side of things of physics. But I do find the various phenomena of space quite interesting.
Okay, excellent. Rutuja, I think, yeah, Rutuja.
Hello everyone, I am Rituja. I'm from Pune as well, and my major is physics, but I'm really interested in radio astronomy and evolution of the galaxies.
Fantastic. Bhargavi?
Good morning, sir. I'm actually from second year.
Okay.
So I chose this elective because I want to pursue my master's in astrophysics.
Okay.
So that's the sole reason why I chose it.
Okay. So Bhargavi, where are you from?
Yes, I'm from Pune as well.
You're from Pune as well. Fantastic. So we have a lot of Punekars here.
Yeah.
Ananya?
Good morning, everyone. My name is Ananya and I'm from Pune, and I'm currently in third year, and my subject of major is physics. And I chose this elective because I enjoy learning more about astronomy and astrophysics, and I hope to learn more about it.
Okay, thanks very much, Ananya. Fantastic. Somesh?
Morning, everyone. Myself, Somesh Karwage, and my major is physics. I like the subject astronomy, so I was selected this as an elective, but like astronomy. It's basically the subject I want to make a career in. So that's why I'm looking forward to learning from Dhruba J Saikia as much as I can.
So Somesh, you are also from Pune or?
No, sir. Actually, my hometown is Buldana, but
okay.
I study university. Yeah, like in a hostel.
Okay. Okay.
Thank you, sir.
You're welcome. Then we have Daniel.
Hello everyone, I'm Daniel Joby and I aspire to be a theoretical physicist, and astronomy is a fallback career option to me, but it's still very interesting. I mean, I've been interested in it since my childhood. I'm basically from Kerala but was raised in Indore.
Then whom I missed quite a few so far. Preeti?
Hello everyone, I'm Preeti. I'm from Ahmednagar, Sangamner. My major is environmental science, but I was a bit curious about astrophysics. That's why I chose this.
Okay, excellent. Okay, then we have Neeraj.
Good morning, guys. Myself Niaz. I'm from Pune. My major is geology, and I choose astronomy because of I watch a lot of movies.
Okay, excellent. Neeraj, Ekta.
Hi everyone, my name is Ekta. I am from Pune, and I've always had an interest in astronomy. So I figured that this is something that I want to learn more on. I have picked chemistry as my major.
Okay, excellent. Okay, you'll realize that as we go along, there are a lot of interrelationships between different disciplines, whether it be geology or chemistry and astronomy, biology as well. Mansi, we have.
Yeah,
Mansi,
I've already introduced myself.
Yeah, I know. Vishaka?
Greetings. It's Visakha and I'm from Pune. And I'm currently doing my third year in BSc, and I have chosen the astronomy as my elective because I've always been interested in the space exploration and to know about, to get more information about the universe and everything. So I chosen this as astronomy.
Thank you, Vishaka.
Thank you.
My name is Sakshi and I am from Samari, and I am interested in. Thank you.
Okay, thank you, Sakshi. You seem to be having some internet issues, no? Harsh Shitole?
I am Harsh Shitole, and my major is environmental science.
Okay.
But I am interested in astronomy because it's quite interesting to learn about the origins of planets, and yeah, I don't know. There are multiple aspects that I cannot tell from top of my head. So
okay, sure. And feel free to sort of interact as you go along. And, so far we have looked at the universe across the electromagnetic spectrum. We have looked at what it looks like starting in the optical, infrared and ultraviolet region of the spectrum. Then we went to the low frequency regime, and we looked at what the universe looked like at radio frequencies, which was the first major part of the electromagnetic spectrum, which was opened up for radio observations due to the serendipitous discovery of radio waves from the center of our galaxy by a radio engineer working at Bell Labs called Karl Jansky. Then we had looked at the high energy part of the spectrum, gamma rays and X-rays. We looked at their discovery, and we looked at a variety of high frequency or high energy phenomena, which gives rise to electromagnetic radiation at the highest energies. So today we look at another component of the universe, another component through which we study the universe. And today's discussions will be based largely on particles. So although these were called rays, these have been called rays, this is more for a historical reason because initially they thought they were rays, but they are actually very high energy particles. So let's see how that has come about, and we'll look at a few aspects of it. Since all of you are from a variety of backgrounds, during this entire course, we have tried to minimize the amount of maths, so it will be largely descriptive, and maths will be used only to illustrate simple concepts or dependencies which we have to take care of while trying to understand the physical processes that are going on. So let me start with a little bit of history, which is the discovery of radioactivity. In the previous classes, we talked about Rontgen's discovery of X-rays and the X-ray and how the universe looks in the X-ray region of the electromagnetic spectrum and extremely high energy phenomena, which one associates with the emission of these very high energetic photons, which are in the MeV range and mega electron volt and kilo electron volt ranges. Now, with the discovery of X-rays, there was an increased interest in these rays. And one of the aspects which led to the discovery of radioactivity was to understand this X-ray emission. Henry Becquerel has been experimenting with fluorescence and phosphorescence, which is luminescence of metals or minerals exposed to radiation, which absorbed light and re-emitted that in longer wavelengths. And what he found was that with the discovery of X-rays, what he was really trying to get at was trying to see if the uranium salts, which he was experimenting with, if he exposed it to sunlight, whether he could sort of study these further in the effects of solar radiation on his uranium salts. And he sort of, saw signatures in his films, which he assumed to be the case due to the sun. But just by accident, what happened on a cloudy day was that, he couldn't do his experiments. This was in the early part of 1896. And he packed it away. He packed it away in his drawer, wrapped it up, went home. And later he came back a couple of days or so later and developed the photography. And he found that, well, they still had the signatures of the photographic film carried the signatures of radiation affecting them. And then he began to wonder that it was not the sun really. So uranium emitted radiation without an external source. So this radiation was different, was different from X-rays because these were reflected by a magnetic field. Now, you know that electromagnetic radiation consists of oscillations of the electric and magnetic fields traveling in vacuum at the velocity of light, and they don't consist of charged particles. But what Henry Becquerel discovered was the particles, the radiation which was detecting, radiation within quotes, were deflected by a magnetic field. So these were really charged particles. And this was what led to the discovery of radioactivity. Marie Curie, her husband Pierre Curie, played leading roles in it. Marie Curie isolated polonium, radium, along with her husband Pierre Curie. And this heralded the discovery of radioactivity. But it must be sort of mentioned that historically, sometimes discoveries are made earlier, but doesn't get quite the attention it deserves because it may not have been the right time. It doesn't take the community by storm. And in fact, the effect of uranium salts on photographic emulsions was recognized by Nipsey de Saint-Victor, a French photographer and inventor, before Henry Becquerel's discovery of radioactivity. In fact, he notes Nipsey de Saint-Victor. He mentions about Henry Becquerel's father, who was also, an expert in these areas, particularly phosphorescence, luminescence, where minerals absorb light and re-emit at longer wavelengths. But why am I telling you about radioactivity? When the topic for our discussion today is not radioactivity, but cosmic rays. That'll come clear in a moment. But let me just, before that, highlight a couple of other things. Marie and Pierre Curie discovered the existence of the elements radium and polonium while doing research on pitch blende. And Ernest Rutherford studied the penetration of these components which are emitted by radioactive elements, and he identified this as alpha radiation and beta radiation. Beta radiation penetrated further than alpha radiation. And a couple of years later, Paul Villard discovered gamma radiation from radium salts. These are more penetrating than alpha radiation and beta radiation. And also they were not reflected by the magnetic fields. It took several years more to realize that the alpha particles were nothing but the helium nuclei of helium atoms. Beta particles were electrons, and what was called gamma radiation over here by Paul Villard were nothing but the highest energy electromagnetic waves, which we have already discussed in one of our earlier lectures. So now you begin to wonder, why are we discovering or discussing radioactivity at all, and then rather than cosmic rays? That connection will come clearer when we sort of mention and look at the historical development of the field. You all must have played around with an electroscope. I mean, if you take an isolated bottle at your home, pick up two sort of silver foils or metal foils, and then put it in a way which is shown in the figure and charge it from top. You can rub a plastic on your hair and charge it. You'll find them slowly separating. But obviously, this is a very crude form of what I'm telling you. They were very sophisticated forms of electroscopes which are built. But what they found was that when they charged up an electroscope, it tended to discharge. And they experimented with various aspects of it. For example, if you put it at a very low pressure, then it discharged much more slowly. So clearly, it meant that the air in it had something to do with the way it discharged. And it was Rutherford and others who suggested that this is probably due to radioactivity. That in the earth, you have a lot of radioactive minerals, and radioactivity ionizes the material or the gaseous gas over there, air over there, and this slowly leads to the discharge, and these boils don't keep separating. Now, Theodor Wolff, our father, he was a Jesuit priest who was a student of Nernst theorem physicist and mathematician. And he also taught for several years at some of the leading institutions. He built quite a sophisticated electrometer and electroscope of his time. And he wanted to find out whether it is really the radioactivity which is responsible for it. In fact, he went all over he went to several places. And one of the things which he did was that he climbed up the Eiffel Tower right to the top and tried to see if the ionization went down, at what rate did it go down, and what was the inferred density of ions. So the ions did fall, and apparently some of the material at the top of the tower was also a bit radioactive, which contributed to it. It fell, but it should have fallen far more. And this was one of the early suggestions to suggest that there was something which was affecting the discharge of electroscopes, which was not related to natural radioactivity on the Earth. Well, Father Wolff went up the Eiffel Tower, but Victor Hess did a little better than that. Victor Hess went up in a hot air balloon in 1911-12. He went up about 5.3 kilometers. And lo and behold, the ionization actually did not decrease, but it actually began to slightly increase. And this was demonstrated more convincingly by Werner Kohlhurster, another German physicist. And his contributions are generally not recognized. Victor Hess got a Nobel Prize for it. But it appears if you look at, yeah.
On the last slide, with the Jesuit priest, why did he expect that the ionization rate would fall as he went up higher?
Because the thing is that if it is due to the natural radioactivity from the ground level, from natural
Okay.
radioactivity, that's going to go down as you go further and further away from the Earth, right? So the easiest thing he could do was to climb up Eiffel Tower, which was quite a landmark and still continues to be a very important landmark in Europe. So he didn't go up in a balloon, but he tried to get away from the Earth from the surface of the Earth by climbing the Eiffel Tower. All right. Okay. So Walter Botte and Cohorster, they also developed what is called a coincidence technique. They sort of shielded their detectors from natural radioactivity, and they said that if particles were really coming from the outer space, then if they had two Geiger-Müller counters, one below the other, and then you would find that one should sort of get triggered before the other. They also put a gold block in between, so that if there was some other reason by which an electron got knocked off, which was not energetic enough, then it would probably get absorbed in the gold block and not reach the lower counter. So they were looking for really high energy particles, which would actually strike both the Geiger-Müller counters, one at the upper part and the other at the lower part. This was a clever experiment which demonstrated that you had very high energy particles coming from outer space. So both Victor Hess and Werner Cohorster made fundamental contributions to realizing that these were energetic particles, that these were indeed charged particles. These were indeed charged particles. They were not high energy gamma rays, which we have talked about earlier. So we have extremely energetic charged particles which are entering our atmosphere. Okay. Now, these were the highest energy particles that were available to physicists at that time. So today we have accelerators which accelerate energy or particles to high energies, whether it be at CERN or elsewhere. But from the 1930s, from the early experiments of Hess and Cohorster to the early 1950s, the cosmic ray particles were the natural source of high energy particles. And even today, when you go to the highest energies, as we shall see in a short while, that cosmic rays are the source of high energy particles. Accelerators can only accelerate particles to a level of energy which is far, far lower than what nature is able to do. And with this opening up of the high energy window, high energy particles, several important discoveries were made. In 1932, Carl Anderson discovered the positron from cloud chamber tracks. And cloud chambers on the right is shown the figure from Anderson's 1933 work, where he reported the discovery where he published the discovery of the positron. And what he tried to show was that this particle comes from the bottom over here in this plate, and then there is a lead plate over there, and the positron interacts with the lead plate and loses energy, so it is curved, and it gets curved by the magnetic field over there, and the curvature tells you that it is not really a proton. Okay, it's not really a proton. It has to be far, far, far less massive than that of a proton to give you the kind of curvature which you see over here. 1936, Anderson and Zettmeyer discovered the muon. Rochester and Clifford discovered the kaon. These are all fundamental particles. Cecil Powell developed the photographic emulsion techniques. Geiger counters, ionization chambers, cloud chambers were used. And then Cecil Powell developed photographic emulsions and discovered another fundamental particle, the pion. So high energy particles were created and within the Earth's atmosphere by secondary sort of reactions due to extremely high energy particles coming from outer space, even beyond our atmosphere. So these were recognitions in the very early days. And as you can see, that opening up we saw in the last several discussions we have had, that how every window of the electromagnetic spectrum that was opened up led to new and fundamental discoveries, new kinds of exotic objects which we were not aware of earlier, whether it be pulsars or quasars or blazars or X-ray binaries, name it. And today we are discussing cosmic ray particles. And you can see that cosmic ray particles have actually contributed fundamentally to our understanding of physics, to discovery of some of the fundamental building blocks of the elementary particles which make up the universe. Now, the question one can ask oneself of cosmic ray particles is, what do they consist of? You can ask yourself, how energetic are these particles? And you can also ask yourself, where do they come from? Okay. And as I just mentioned, cosmic rays observed on the surface of the Earth are secondary or higher products of high energy particles entering the upper atmosphere. Because once these apart, some of them may reach the ground, the highest energy ones, but many of them would interact with atoms in the atmosphere, leading to generation of secondary particles. In fact, what are called cosmic ray showers or air showers. So when you want to find the pristine abundances of these elements, one will need to know the physics of these interactions and make corrections for the interactions with the Earth's atmosphere. And this is one area where rockets and satellites have helped also revolutionize the field, because they could go outside the atmosphere and try and measure abundances of these cosmic ray particles. But the highest energy cosmic rays are still ones which we can only detect from the Earth or have detected from the Earth. And I will come to that and we'll see why that is the case. But before that, what do they consist of? Okay. What do they consist of? They consist largely of protons, okay, which are the nuclei of hydrogen atom. They contain of alpha particles, nuclei of helium. They contain a small amounts of heavier elements, nuclei of heavier elements, carbon, nitrogen, oxygen, and heavier elements. They consist of a small fractions of electrons and positrons, and the bulk of these are actually electrons rather than positrons. Now, on the right, what I have shown is an important graph. So I'll not erase through it very much, but I will sort of highlight some of the aspects to you. What on the y-axis over here gives you the relative abundances of elements. This particular figure, which I've taken from a paper by Horandel in 2007, has fixed it at at 100 for silicon. I think, yeah. Z is equal to 14, atomic number 14, and that's over here, and fix it at 100, so that you see the relative abundances. This 14 is 100 or 14 is sort of arbitrary. You can fix it on other elements as well and look at the relative abundances. So what you can see over here is that these great triangles which you see, they are measurements of abundances in the solar system or solar neighborhood. These are the gray-filled triangles, right? And the rest are all observations of cosmic rays. Okay? So just sort of remember that the gray triangles are from the solar neighborhood, which are solar system values, and all the others are from cosmic rays. And these are actually from different experiments and missions. You can see that some of these are from spacecrafts, High Energy Astrophysics Observatory, Ariel 6, etc. Okay, so both ground-based, particularly at the highest energies, you have ground-based ultra high energy cosmic experiment. And what I would like you to notice is that when you look at hydrogen and helium, the two most abundant elements in the universe, okay, that the cosmic rays are actually underabundant for hydrogen and helium. Okay, they are underabundant, and these are not factors of 1 or 2 within the errors of measurement. Over here, you can see it's 10 to the power over 10 to the power of 6, and this is close to 10 to the power of 5 for hydrogen. So it is more than an order of magnitude, more than 10 times less. The other aspect, I'll just point out a few of these, not too many. Okay, you can see again over here that cosmic rays are overabundant over here. These are the lighter nuclei, okay? Lithium, beryllium, boron, okay? And then again in elements over here, okay? In the 20s, we'll see that in more detail in a short while. It is again overabundant. And in the 60s, again, it is overabundant. And a lot of the regions, it is sort of within the error bars, it keeps fluctuating. But these are some of the systematic trends which one sees when one looks at the abundance of cosmic rays. Now, why does it happen? As we just mentioned, just to recap, underabundant in hydrogen and helium, overabundant by several orders of magnitude. You can see, yeah.
What's the difference between galactic cosmic rays and cosmic rays from the solar system? Is it just that their origin? By galactic, do you mean outside the solar system? And if so, how can you tell?
Yeah. Galactic could be from anywhere in our galaxy. In fact, we'll see later today that the ultra high energy cosmic rays are probably from even outside our galaxy. But our sun itself also gives off cosmic rays, and these are usually at the low energy end. Okay. But these abundances, when I mentioned solar abundances, these are not cosmic ray abundances. These are abundances which are measured for the sun itself, meteorites, and the interplanetary medium. Okay, so these are
these cosmic solar system values? Are those of the preponderance of elements just as stuff in our solar system, or as cosmic rays?
No, these are as stuff in our solar system.
Okay.
Okay. When I say solar abundances, their solar system as matter constituting the solar system. All right. And everything else is cosmic rays, which includes cosmic rays which come from the sun as well. Okay.
Okay.
All right. Okay. Now you can see that there is overabundance of lithium, beryllium, boron. Then, as I mentioned, 21 to 25 or so, scandium to magnesium. And over here again in the 60s from neodymium to yttrium. Okay. Now, an interesting question to ask oneself is, why does this occur? Why do these occur? And we'll look at a very qualitative description, although there are more detailed treatments of it as well, which are more mathematical. See, most of the cosmic rays we'll see later, particles which are generated, because these are very high energy particles, they're generated in very energetic events, which could be like, for example, supernova explosions. And supernovae produce a lot of heavier elements, and they're usually underabundant in hydrogen and helium. So because of the production of these high energy particles in energetic events, which may be underabundant in hydrogen and helium, that is at least partly responsible for the underabundance of hydrogen and helium. But when you look at the overabundance of elements, whether it be lithium, beryllium, boron, or whether it be the Z equal to 21 to 25 or 60 to 70 atomic number range, these are believed to be due to fragmentation of heavier elements, and which get broken up into smaller elements because of interactions with high energy cosmic rays. Okay, a term called spallation, which is used, where particles get bombarded, where heavier atoms get bombarded by high energy particles and get broken up into smaller elements. So you can see the abundance of cosmic rays is related partly to the production process and partly to what happens as it keeps traversing in interstellar or in interstellar space. They get knocked about as well, or they can get knocked about and break up. The heavier nuclei can break up, particularly the ones which are a bit more unstable can break up into smaller nuclei. If they're very tightly bound and stable, it's more difficult to break them out. But you can see that there's a whole range of elements which can form by breaking up of heavier nuclei through interactions. Now, how energetic are these events? How energetic are these particles? Some of you may be familiar with these notations, but I just sort of thought I would put in a slide to highlight the kind of energies or the numbers which are used. Kilo you'd be familiar with, mega you'd be familiar with, giga you'd be familiar with, okay? Then we go into higher and higher energy levels, okay? 10 to the power of 12, 15, 18, which is called exa. And just to remind you, an electron volt is the amount of energy that one electron gets by accelerated by a potential of 1 volt. So you can see that when you look at the energies, the highest energy cosmic rays are about 10 to the power of 20 electron volts. And as I mentioned, high-end energies in CERN are typically close to about 10 to the power of 13 electron volts. So when you're looking at the highest energy cosmic rays, they are in fact orders of magnitude larger than what you can produce in in our accelerators on the Earth. So in terms of probing the high energy cosmic rays, high energy particles, that you still have to deal with cosmic rays. Although there have been a lot of interesting experiments and discoveries made by the accelerators, but when you want to study the highest energy particles, cosmic ray particles are the source. In fact, when in 1991, there's this fly-side telescope at Utah, which detected this particle of 3.2 into 10 to the power of 20 electron volts. It was called as "oh my God" particle because that was the reaction they had, "oh my God." And there are very few of them. We'll see in a short while. But there are a number of events. There's another one which was developed, which was detected a little later, but at about 2 times 10 to the power of 20, and there are a few more known now. So cosmic rays, you can see, have a large energy range. We'll look at the spectrum in a short while. And at low energies, the observed spectrum is also modulated by the solar wind. Solar wind are effectively charged particles, which are constantly flowing out from the sun. At energies greater than about 10 to the power of 9 electron volts, the spectrum can be described as a power law. This is the way particles actually we saw keeps getting accelerated in supernova remnants, in the lobes of radio galaxies, and giving you a power law kind of spectrum. This is where P is 2.5 to 2.7. So the higher the energy you go, the fewer the particles that are there. So that in a log-log plot, if you plot it, it looks like a straight line. So this is the spectrum, just to show you. You can see this is about 10 to the power of 9 is at the lower end of the spectrum. Okay, this is 10 to the power of 9 over here. And you can see 10 to the power of 20 over here. Okay, and at the lowest energies below about 10 to the power of 9 or 10 to the power of 10, the number of cosmic rays which you would receive gets modulated by the solar wind. And that is, as I said, high energy particles coming out from the sun. And in this particular range of less than about 10 to the power of 10 electron volts, most of the energy, most of the cosmic rays are from the sun itself. Okay. Now, if you compare this energy to that of the rest mass energy of a proton, that if you take m0, the rest mass energy multiplied by c squared, the velocity of light, Einstein's famous equation equal to mc squared. So you'll get about 938 MeV. MeV, as we saw, was 10 to the power of 6. So you can see that, and these, as we saw earlier, that most of these are protons, right? 90% of them are protons, and approximately. And you can see that when these are the energies that you're talking about, you can go and calculate what the Lorentz factors are and what the velocities of those particles would be. Because the energy E is equal to, this is the rest mass energy which I have written, which is the rest mass m0 multiplied by the square of the velocity of light. When you want to find out the energy, E is equal to gamma. Gamma is the bulk Lorentz factor, which is given by 1 upon square root of 1 minus v squared by c squared. And if you put in the energy as whatever, 10 to the power of 17, 18 electron volts, and you know the rest mass of the electron, you calculate what the velocity should be, you'd find that they are almost traveling at the velocity of light, okay, to many, 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 many decimal places. So you have particles which are being accelerated. Yeah.
By flux, do you mean from below me and above me? Do you mean the total below or above me, or for each point?
Yeah. Okay, I'll come to the knee in a short while, Aquino. Okay, all right. I'll come to the knee in a short while. Okay. Now, okay. So you can calculate the Lorentz factor to it. So I would actually suggest that you do it yourself, and you will find the energies to which these particles are accelerated. I mean, protons are accelerated to velocities which are, almost the speed of light. Okay. Now, although I mentioned that the particles have a power law slope, cosmic ray physicists actually spend a lot of time to understand the generation of these particles. Also, the slopes are slightly different. one of the features which was identified quite early on is called the knee. Above the knee, it is slightly steeper, and below the knee. Okay, so now why do these differences arise? Is something which perhaps has to do with the origin of cosmic rays, the way particles are accelerated, but it is something which cosmic ray physicists work in great detail to find out. And there is also claims of a second knee over here, and there is an ankle which is not very clear in this. It's slightly clearer, but I'll show you another place where it is clearer. Okay, when we talk about flux, okay, in response to your question, we're talking about the number of particles per meter squared, per steradian, per unit of energy per second. All right. So for example, when I plot a point over here, it would mean that the number of particles which are coming over here, if you had a detector of 1 meter squared coming from 1 steradian in the sky, per unit of GeV in energy and per unit time. Okay, so that is what each of these points represent. Okay, that is the way conventionally fluxes have been denoted, and you can see that many of these from the label over here, you can see some are satellite, some are ground based, and as you go to higher energies, Aquino, which you mentioned earlier, that is a ground based detector, and when you go to the lower energies, it is more spaceborne. Okay. Now, at less than about 10 to the power of 10 electron volts, solar contribution and also solar wind modulates it. And there are all kinds of exotic phenomena which takes place on the surface of the sun. For example, there are what are called coronal mass ejections, where material is shot out from the surface of the sun at velocities which could be many hundreds kilometers per second, carrying a lot of energy outwards. And these coronal mass ejections can affect communication if it hits the Earth. And these solar weather, as it is called, is of great interest, not only for everyday things. For example, there was one very strong one which once burnt down a power station in Canada, but also communications generally, spacecrafts, effect on satellites. So all these are important aspects of understanding these. But in terms of cosmic rays, these actually affect the spectrum at low ends. So these actually have a dependence on the solar cycle, because when the sun is active and there are more sort of sunspots, there is more activity, then you will see lesser number of low energy cosmic ray particles. At greater than about 10 to the power of 10 electron volts, these are largely believed to be energetic events in our galaxy itself, while at the highest energies, it could be even from outside our galaxy. Okay, so you can see these cosmic ray particles that we detect over here on the Earth. Some have in fact traveled very long distances from our neighboring galaxies as well, besides coming from the distant regions of our own galaxy. This figure also shows you the kind of energies which particle accelerators have achieved. And you can see that when it comes to the highest energies, they are way below what we have been able to achieve with particle accelerators that we have built. This one just shows you a little bit more detail, a blown up of the ankle, plotted in slightly different units over here to highlight the fact that there are indeed changes. And there are suggestions that, that they're the natural candidates for the ankle is a natural candidate for the boundary between what are galactic cosmic rays, that means cosmic rays which originate in very energetic events in our galaxy, to extragalactic cosmic rays, which could come from energetic events, including active galactic nuclei, which we talked about while discussing the electromagnetic spectrum. A few more aspects about cosmic rays. Cosmic rays are largely isotropic, and we'll see why that is the case. They're also approximately roughly constant in time, except for the low energy part of it. Okay, and this is an experiment which shows the sunspot numbers. Okay, they have been multiplied, but one needs to just see the trend over here. Okay, and when you can see that there is an active sun, which means that there are more sunspots, there is greater solar activity, there is a dip in the cosmic ray particles that we detect. This is from an experiment which is going on in the Antarctica. Okay, And when it is a solar minimum, as we call it, when the number of sunspots is low, there is less solar activity, then you'll find that the number of cosmic ray particles go up. And this is at the low energy end, where the cosmic ray particles coming from elsewhere gets modulated by the solar wind. Now, as we said earlier, at low energies in the Seer spectrum is dominated by solar cosmic rays. At higher energies till the knee and possibly the ankle, energetic galactic phenomena. Now, what are the energetic galactic phenomena that could do that? One is supernovae, where massive stars end their lifetimes in explosions releasing about 10 to the power of 53 ergs in energy. We saw that supernovae are detected at tera-electron volts in gamma rays and also from supernova remnants. They're also very massive young stars. These stars are called Wolf-Rayet stars, and there is one such example which is shown over here, and along with the example of the Vela pulsar, along with its wind nebulae and a jet-like emission which is coming out from the pulsar. And pulsars, gamma ray pulsars we talked about, some of which are not even observable in the radio region of the spectrum. Pulsar wind nebulae, where young pulsars drive off winds, strong winds. These are all sources of high energy particles, high energy photons, basically the high energy part of the universe. And beyond the ankle, we believe these are believed to be of extragalactic origin. Why we say that, we will see in a very short while. This will involve just a very little elementary mathematics, which you would all be familiar with, I'm sure, but I will go through it a bit more slowly. As I promised, wherever there's an equation, I'll go a bit more slowly. Now, can we say where a cosmic ray comes from? To try and find out where a cosmic ray comes from, first thing is to estimate the Lama radii. You know that when a charged particle is moving in a magnetic field, it will have a helical orbit, and you can find out the orbit by equating the Lorentz force on a charged particle. This is motion in a magnetic field. I've taken, for simplicity, a perpendicular component. So I've omitted sine theta terms, but it would have been a vectorial of Q into V cross B, but VB sine theta, theta 90, so VB. And this is the centripetal force. I've just equated the two forces, gamma, because these are moving at highly relativistic velocities. So you need to take the relativistic correction to the mass. And gamma, as I mentioned, is 1 upon square root of 1 minus V squared by C squared. Q is the charge. And you can work out what a radius is. Okay. And if you take velocity is of the order of C, you can, which is true as we saw for almost the entire range of the cosmic ray spectrum, you can try and calculate what the radius is. Okay. So in a field of 1 microgauss, okay, which is 10 to the power of minus 10 Teslas. Okay. Now 1 microgauss, why have I taken? Because that is expected to be the typical magnetic field in a galaxy. Okay. So we have a proton of 10 to the power of 15 electron volts, say. It has a radius of about 3 into 10 to the power of 16 meters. You can verify that for yourself in case I've made any sort of silly errors, but these are typically sizes of supernova remnants. So if the Lama radius is very small compared to the typical sizes, it will remain confined, but if the Lama radius is larger, it will not be bound, it will escape out of that component. And also particles, all these high energy particles will be scattered by magnetic fields, irregularities in the interstellar medium, and they'll have a very ragged path. And this is not very different from the way a photon comes out from the center of the sun. For example, you know that energy in the sun is generated by nuclear reactions. And this energy is generated in the center of the sun because that is where the densities and temperatures are large enough for nuclear reactions to take place to sustain the energy generation in the sun. And how does this photon come outwards? By basically a random walk. It'll keep bumping into particles. It is not the same photon which will come out. It may excite something, it may, which will emit another photon, but basically it comes out via a random walk, which takes thousands and thousands of years to come to the surface from the sun. Similarly, these high energy particles, as you can see on this slide, will come from a distant source, will keep bouncing against different irregularities, and ultimately reach you. And because the magnetic field in our galaxy is random as well as uniform, and a lot of irregularities on different scales, that as it moves around, it is very difficult to know where it has come from. So you cannot really know the source of most of these cosmic rays. The very high energy particles may be affected a bit less, but it is generally difficult to find out where a particular cosmic ray particle that you've detected, which is the source of that inner galaxy. This is just to show you what this is of a different galaxy, not our own galaxy. This is to show you magnetic field directions. You can see that there is some uniformity. So there is a uniform component, but there is also a strong random component in the magnetic fields of spiral galaxies, driven by a very turbulent interstellar medium. So one thing to remember is that it's difficult to pinpoint where a cosmic ray particle is. For example, when I look at a star, I know where the star is because the light is coming straight towards me. There may be minor effects of refraction and scintillation and diffraction, etc. But I know the direction from where the photon has come from. But when it comes to cosmic rays, I don't have a clue actually where it has come from, because it has had a very sort of random walk through the interstellar medium of the host galaxy. So while it is random, there is a very small anisotropy, which was noticed quite some time ago, but has been sort of established more recently by, more firmly by the Pierre Auger Observatory. And it's at a very small level of about 7% or so. And this is only at the highest energies, about 10 to the power of 18 or 10, close to 10 to the power of 19 electron volts. And the thing is that, again, you can see that it is, there is a large anisotropy. And it's difficult to actually pinpoint a source for it. But what people have done is they've tried to build detailed models of how that might originate, given that if it had an extragalactic origin, which is believed to be the case for these very high energy particles, that we have our own galaxies located in a local group, which is part of a larger cluster, a larger supercluster. So taking all this into account, then can we actually model it in terms of our galaxy, and assuming also an intergalactic magnetic field? I said earlier that our galaxy has a magnetic field typically in the range of a microgauss, whereas if you look at the intergalactic magnetic field, it is of the order of a nanogauss. So detailed modeling has shown that that these galaxies, these very high energy cosmic ray particles, where they exhibit a mild anisotropy, may be due to the distribution or the energy sources in our nearby galaxies, guided by interstellar, not interstellar, but intergalactic magnetic fields at nanogauss levels. So now I'll come back to the spectrum again, just to show you schematically and illustrate to you why it is difficult to detect the highest energies from space. And that is because of just the density of particles which you actually detect. Okay. Now, a rough sort of guideline is shown in this plot over here. Okay. Again, relative particle flux in logarithmic units. Okay, in about 10 to the power of, over here, 10 to the power of 10, 10 to the power of 12 range. It is about 1 particle per square meter per second. Okay, so that's a good flux, right? So if you had a detector in space, you'd be able to, detect a fair number of particles. Now, once you go to about 10 to the power of 14 or so, 1 particle per square meter per year. So it's getting difficult, but 10 to the power of 13, 14, people have done it, but it gets to be a bit of a challenge. Now, once you get to orders of 10 to the power of 18 or 19, you get 1 particle per square kilometer per year. So there's no way you're going to build these huge detectors in space and wait for a year to detect a particle. It's just not feasible. So when you are talking about the highest energy particles, you actually use the air, the atmosphere itself as a detector. So far, while talking about the electromagnetic radiation that we receive, we have been talking about the atmosphere more as a nuisance because it blocks off photons at both high energies, X-rays, gamma rays, ultraviolet, optically it comes through, then radio waves at the lower end, ionosphere cuts it off. So we talk about the atmosphere more as a nuisance, but here actually we are using the atmosphere to try and detect these high energy particles. And how do we detect them? We detect them because these high energy particles give rise to what is called an air shower or a cosmic ray shower. They interact with particles in the atmosphere, generating a whole cascade of millions of other particles. And the number of particles and the nature of particles will depend upon the energy of the incoming particle. And here, just an illustration of a shower. And you try and detect this shower with Earth-based telescopes. So this is another sort of illustration of the same thing. Okay, how many cosmic rays strike the Earth? This gives you the same concept which I mentioned earlier, 1 GeV, about 10 particles per square meter per second. As you go to higher and higher energies, it keeps getting lower and lower. 1 particle per square meter per second. 10 to the power of 16, few particles per square meter in a year. 10 to the power of 18 per square kilometer per year. And when you go to 10 to the power of 20, it's a per square kilometer per century. So you need, to decrease the time. If you don't want to wait for 100 years, you really have to increase the area over which you want to detect it to be able to detect the highest energy particles. And to just give you an idea, a 10 to the power of 11 GeV could produce about 100 billion particles. So you have particles detectors which are spread all over, on the surface of the Earth to which you detect them. They could be Geiger cube, they could be scintillation counters. And then because these particles would generate, these incoming particles generate a whole range of high energy particles, that these particles could be moving higher than the velocity of light in the medium. Okay. And if it is traveling at a velocity which is greater than the velocity of light in the medium, then you would get what is called Cherenkov radiation. So these charged particles will also give rise to Cherenkov radiation. Pulses of radiation, which these telescopes over here, for example, these light pulses, can be picked up. In the focus, you'll have photomultiplier tubes, which will multiply the signal many times and then try and detect it. These high energy particles can also generate very high energy muons. And sometimes you have these muon detectors deep underground because they are going to penetrate much further, and you don't want to be get rid of those which would be detected higher up and would probably be absorbed before they reach deep down. So there have been a number of these observatories. We will not get into too much of detail in an introductory course, but just to introduce you to 1 or 2 of them. This is a Pierre Auger Observatory, whose results I mentioned earlier. In the early days, for example, ionization chambers, Geiger-Müller counters, cloud chambers, these were the standard detectors which were used. Cherenkov effect has also become, as we just saw, quite important in terms of detection of cosmic rays. This is an experiment, an Indian experiment, which has been set up by TIFR along with various other collaborators at UTI. It says GRAPES as gamma ray astronomy at PV energies. And they have a whole range of scintillation detectors over here. I've left it as an exercise for you to find out a little bit more about GRAPES. And I've also given a link to a YouTube video by Sunil Gupta, my friend and colleague from TIFR, who gave a talk on this experiment for one of our programs. And this is another detector, Super Kamiokande in Japan, which actually has huge tons, 50,000 tons of ultra pure water and this actually detects neutrinos, which can give rise to by various nuclear reactions into electrons, positrons, and these traveling at faster than the velocity of light over water would give rise to Cherenkov radiation. And these photomultiplier tubes pick up the light signals from this Cherenkov radiation. And you want to sort of minimize other sources which might give rise to radiation, which you want to minimize. So you build these detectors deep underground. This is about 1 kilometer underground. So you can see that it's an exciting area of high energy physics. And I will end today's thing by just illustrating one important effect which has been mentioned, which has been worked out. We will not go into the mathematics of it, but just illustrate the physical aspect of it, which was pointed out by Kenneth Greisen in the US and 2 Russian physicists, Zatsepin and Kuzmin. And what they said was that, okay, you have these high energy protons which are being generated. Is there a limit to which I can be able to detect them or see them? Now, why should this arise? This arises of an interesting effect, because if you look at the protons which are moving, as we just saw, at velocities almost at the velocity of light. Okay? And we also know, and as we saw when we were discussing the radio window of the spectrum, that the relic of the early Big Bang origin of the universe, the cosmic microwave background radiation, which today is at a very low temperature of about 2.7 degrees Kelvin, okay, and permeates all of space. Now you look at a proton, which is coming at highly relativistic speeds. Now, in the rest frame of the proton, what it is going to see is this blue-shifted cosmic microwave background radiation. So it will be shifted to very high energies in the proton rest frame. It can interact with this CMB photons to give rise to what is called a delta plus particle, which will decay into a lower energy proton plus a pion or a neutron plus a plus. And they worked out and said that, well, you know, if you have particles about greater than about 6 into 10 to the power of 19 electron volts, then these particles would be very difficult to detect because they would interact with the cosmic microwave background radiation, reduce to lower energy particles, and you should not ideally have any particles greater than this energy. As we mentioned that we have seen particles of about this energy or slightly above it, which is about 3 into 10 to the power of 20 electron volts. As far as I know, this is still probably the highest energy or close to the highest energy. And on the right, what I have shown is just that, I mean, obviously the chances of these interactions also depend on how far the cosmic ray is coming from, because if it is coming from a far enough distance, the chances of interactions would be more. So there's a limit to the distance from which these high energy particles come from. And that is what is illustrated in the figure which I've shown over here. And they have done detailed experiments on how it would differ for different species, etc. But you can see that beyond about a couple of 100 megaparsec, it will be very difficult to detect these protons. Now, the other related question to this is, I mean, there is a drop, that is true, and there are very few particles over there, but is it the GZK effect, or is it difficult for nature to produce such high energy particles? So I don't think one has a definitive answer to that, because you can see the amount of energies that are involved in this. We are familiar with 1 electron volt. I mean, this is 10 to the power of 20 times higher than that, and you get in a square kilometer probably one such particle in a century. That's the kind of particle that you get. So whether it is a GZK effect playing a role, or whether there is a genuine difficulty in generating such high energy particles, as far as I'm aware, the jury is still out. But as a physical effect, the GZK effect is an important aspect of our study of high energy particles that we need to bear in mind.